Today we will learn about work and kinetic energy. In physics we say work is done only if an object is moved through some displacement while a force is applied to it. So we have our work equation where we have our force times our displacement will give us the amount of work done. And in order for work to be done, the force and the direction of the displacement have to be in the same direction. And we can express work in the unit of joules or Newton centimeter. We can see that force can be split into two components, one parallel and the other perpendicular to the direction of displacement. So we see that force is a vector quantity. However, only the component parallel to the direction of displacement does work on the object. So we see that our equation for work is force times cosine of theta times our displacement. When work is done on an object, the object put into motion. This motion is called kinetic energy. The kinetic energy of an object is its mass moving with a velocity. We see that kinetic energy can be defined as 1/2 times our mass times our velocity squared. We can see that kinetic energy, just like work, is expressed in the unit of joules. So we see here we have an example that states a student pushes on a heavy box with a force of 400 newtons and moves it a distance of 5 meters. If the force is applied at an angle of 37 degrees, find the work done by the student. If we state the information that we're given, we see we have a force of 400 newtons, a displacement of 5 meters, and an angle of 37 degrees below the horizontal. So we're asked to find the work done by the student. So we know work is defined as our force times our displacement. Since we have two components of force, the component of force we'll have to use is the component that is parallel to the direction of our linear displacement. We see that the force applied in the linear direction is summarized in our figure to the right, where we have force times cosine times our angle applied. So our force will be 400 newtons times our cosine of 37 degrees times our displacement of 5 meters. And when we multiply this out, we'll see that the total work done will be 1,600 joules. In our second example, it states an Eskimo pulls a sled loaded with fish. The total mass of the sled is 50 kilograms, and the Eskimo exerts a force of 1.2 times 10 to the second newtons on the sled by pulling on the rope. In part A, we're asked how much work does he do on the sled if the rope is horizontal to the ground and pulls the sled 5 meters. So in part A, if we summarize the information we're given a mass of 50 kilograms, a force of 1.2 times 10 to the second, and a total displacement of 5 meters. We see that our work equation is force times our change in displacement. And since the rope is horizontal to the ground, there's no angle to worry about. So we're given our force of 1.2 times 10 to the second times our change in displacement of 5 meters. If we multiply this through, we'll see that the work done will be 600 joules. In part B, we're asked how much work does he do on the sled if he pulls the sled the same distance at an angle of 30 degrees above the horizontal. So yet again, our mass and our force applied hasn't changed, nor our displacement. Instead, we see the force is being applied at an angle of 30 degrees. If we use the component that's parallel to the linear displacement, we'll have our equation of force times cosine of our angle times our change in displacement will give us the amount of work done. So we know that our force is still 1.2 times 10 to the second times cosine of 30 degrees times our change in displacement of 5 meters. And when we multiply this through, we'll see that the work done by the Eskimo will be 520 joules. In part C, we're asked how much work does he do on the sled if he pulls the sled at the same distance at an angle of 30 degrees above the horizontal, but there is a friction between the snow and the sled. Coefficient of kinetic friction between the sled and the snow is 0.2. And we're asked to find the net amount of work done by the Eskimo. Since we're trying to find the work performed by friction, we'll have work is equal to our friction force times our change in our displacement. And we see that our friction force can be broken into the coefficient of our kinetic friction and multiplied by our normal force times our change in displacement. In order to find n, we see that n is part of the y component. So if we sum up our forces in the y component, we'll have n acting in the positive y direction. And if we take the components of our right triangle, we see that the opposite of our degree will give us sine, which is acting in a negative direction of mg times sine of theta is equal to 0. So now we can solve for n, and if we do so, we see that n is equal to mg times sine of theta. So now we can plug this into our work equation, where we'll have our force, which is our coefficient of our friction force, times our normal force, which is equal to mg times sine of theta, times the parallel component in the direction of our linear displacement, which we can see the force acts in the direction opposite of the force being applied. So the angle created by our friction force will be cosine times 180 degrees times our change in displacement of 5 meters. Now that we have the correct equation, now we can plug in the values that we have been given. So we see that force will be equal to our coefficient of our kinetic friction, which is 0.200, times our mass of 50 kilograms, times our acceleration due to gravity, times sine of the angle that the force is being applied, which is 30 degrees, times the parallel component of our linear displacement, which is cosine times 180 degrees, times our change in displacement of 5 meters. And when we multiply this out, we'll see that the work done by the friction will be a negative 430 joules. And we should expect to have a negative value since our force of friction is being applied in the opposite direction. So we're asked to find the net work done by the Eskimo. So in part B, we found the work done by pulling the sled was 520 joules. And the work performed by friction was a negative 430 joules. We can sum up our net work to get a value of 90 joules. In our third example, we're asked to determine the kinetic energy of a Volkswagen that has a mass of 1,000 kilograms, moving at a velocity of 10 meters per second, and then find the kinetic energy of the Volkswagen if it's moving at 20 meters per second. So, if we find the kinetic energy of the Volkswagen when it's traveling at a velocity of 10 meters per second, we know that our formula for kinetic energy is equal to 1/2 our mass times our velocity squared. So we are given a mass of 1,000 kilograms and a velocity of 10 meters per second squared. We should get a kinetic energy equal to 50,000 joules of work done. And then part B, we're asked to find kinetic energy of the Beetle when it's moving at a velocity of 20 meters per second. So again, we will use the same equation, and we see that our mass hasn't changed, but our velocity has. Instead of being 10 meters per second, we have 20 meters per second squared. And if we multiply this through, we'll see the kinetic energy performed will be 200,000 joules of work.